Okay, the doors are closed, so I think I'm going to start. My name is Brandon Young, and the name of my talk is Reversing All the Malware and Why You Should Stop It. So first, no, I'm not trolling you guys. I'm not telling you to stop reverse engineering. That's not what I want you to do. I'm a reverse engineer. I do it every day. I love it. I encourage everybody to pick it up, at least try some malware analysis, look at some code. You might be able to figure some pretty cool things out. So if I'm not telling you to stop reverse engineering, what do I mean? Well, throughout my career, one of the things that I've noticed, well, first, I've been on a lot of really good teams. And teams that have done a lot of threat intel, a lot of reverse engineering, malware analysis. It's been a common theme. And I've done a lot of threat intel myself. But one of the things I've noticed is whenever a signature hits and we get a new sample, whether it's PlugX, Hansator, it could be Zeus, whatever, the same people are analyzing this malware repeatedly. And we're looking at the same samples every day. You might have some guy who's looking at PlugX or a lady who's looking at Hansator, and that's their one job, and they want to reverse engineer these samples constantly. It's a little redundant, and it's repetitive, and it's a waste of time. So that's basically what the talk's about. In an ideal world, if a signature hits, you should have some type of automated technique to take that file, that piece of malware, and send it through some kind of automated system and determine what the IOCs or what the areas of interest from that sample are for you, and have those pushed back to you immediately without having to actually reverse engineer every single sample. The goal is really to eliminate redundancy. We shouldn't be looking at all these things every time they pop up in virus total with a new hit. So really, we want to help ourselves. So the more you can automate, the less work you have to do and the more time you have to analyze really cool shit. So who am I? I'm a malware reverse engineer. I've done threat intel and malware RE for about 10 years now. I spent a lot of time in the government. Past couple years I've been private sector. It's a lot of fun. Currently with Palo Alto Networks. And who is this talk for? Pretty much anybody who deals with malware. You don't have to be a reverse engineer. Threat analyst, IR, SOC analyst, anybody really who's interested in malware or looks at this stuff, this could pertain to you. You don't have to be a reverse engineer to use automated malware analysis techniques. And you don't have to be a reverse engineer to do malware analysis and look at things. You don't always have to get down to the lowest level of things. If you are a member of a SOC team or an IR team or a threat analyst and you don't have time to do the reverse engineering of this malware, you need to have your reverse engineers automate things for you so you can get the information you need without having to go back to them every single time you get another PlugX sample. And if the sample was reversed one time, please don't continue to reverse it. It's redundant. There's code reuse for a reason. A lot of these malware authors will either reuse the code that they write or they're going to use builders, and we see that all the time. So general overview. Like I said, stop reversing everything in sight. We really don't need to do it. I'm going to go over the current and past RE landscape a little bit of what we used to do, what we're starting to do, and why we're doing that. A couple of automation techniques that I like to use. I'll do some demos and give you a couple of ideas maybe that you can use, and general conclusion. So to start, I want to show basically on the internet we can find reports on almost any kind of malware we're looking for. A couple of friends of mine have a repository on GitHub called APT Notes, and as you can see, I don't know how big that is, but there's over 350 different reports just in this repository. These are APT reports, very detailed technical analysis of APT malware, and it's really a time-saving effort to read some of these, because one of the things you can do is create signatures, you can read about new techniques or techniques that have been used in the past, and these are things that you don't have to try to figure out on your own. If somebody else has already written a report on it, you don't have to, or at least you shouldn't be doing it. They're a valuable resource, and they can really definitely, they can help save in writing signatures. So I want to give a general overview of my approach to malware reverse engineering. Essentially what I like to do is what I call surface analysis. Whenever I get a file, I want to look at the strings of it, essentially because if I can figure out what this malware is before I actually have to dig into it, that's great. And a lot of things like Zeus or PlugX or other things like that have certain strings that are going to be popping up every time you look at them. And you don't have to deobfuscate everything to see it. You should always be looking at the hashes. Google the hash. If you Google a hash and you find something on VirusTotal or on Total Hash or malware and it comes up and says 40 vendors think it's this, well, it's probably that. I mean, 40 vendors didn't screw up, and if they did, maybe, I don't even know. Usually virus total results or multi-scanners are pretty accurate, at least with some of the common things. Zeus, Zbot, it's right. Can I run the malware in my sandbox? I use a sandbox, and the sandbox I use is pretty hardened, so usually things are going to execute in it. I use sandboxes all the time essentially because if I can get good results from it and something can tell me it's malware and it can show me a list of the API calls, then I don't have to go and actually execute this or debug it myself, and it saves a lot of time too. Can I automate the analysis? Well, if I've already seen this malware, if it's plugx, I've got so many scripts and deobfuscation tools that I can use for plugx that I'm never going to analyze another sample myself. It's completely pointless. But if that's not the case, and I actually have to reverse engineer it, then I'm going to start the process. If I really need to dig down deep into it, then it's probably something interesting and actually worth looking at. So for the past 5 years, companies have been very scared of APT. They should be, I guess. We hear a lot of sayings like, it's not if you get breached, but it's when you get breached. And APT are already in your network. Things like that we hear all the time. And it kind of scares people. I consider it a scare tactic a lot of times. It's a really good selling point to sell products. Hey, we know you're infected. You need to let us come in and look at your stuff. It's not wrong. You probably are. But you've probably got I would be willing to guess a high percentage of the malware in your network isn't APT. It's probably adware. It's some kind of grayware that some idiot's going to get again if they double click on whatever or look at porn or whatever they're doing that they shouldn't be doing on your network. And that's kind of been the way things have been for the past 5 years, and even longer actually. A lot of times, since I'm from the government, I don't really get to see what happened in the early 2000s and the late 90s. Most of the time the things I looked at were concealed and undercovered. But so today, the future, we're not as scared as APT, and I think one of the reasons for that is we've got things like ransomware. And let me start by saying ransomware is a complete bitch. If you haven't dealt with it and you have to, you're probably going to get frustrated. The code isn't sophisticated. It's usually not that hard to figure out what ransomware is going to do, and most ransomware families do very similar things. The problem is people that are writing this stuff are getting better at it, and the better they get at it, the more screwed we are. One of the biggest problems with ransomware is we've got people that aren't making backups of their stuff, and they've got network shares connected. And what happens if you get hit by ransomware and you've got a network share? Well, everybody's screwed, especially if you're a developer and you've got shared code, and you go down a rabbit hole, you're in a lot of trouble. So what about APT now? APT is still here. It's cyber espionage. There's always going to be espionage in the world. That's the way government works. That's the way humans work. We want to spy on each other. We want to figure out what everybody else is doing. It's not going to change. Certain things have changed, though. A lot of them have new TTPs, and there are a lot of more custom second and third stage payloads. We don't see as many custom droppers or first stages anymore, just because I think that the enemy, whoever that might be, has gotten smarter, and they realize why waste something custom on a machine that's probably going to be a sandbox or whatever half the time anyway. One of the things we do see is you got a lot of APT team members moving around, and what I mean by that is they're just like us. No matter who you're talking about, I don't care what country they're from, who they are. If it's an adversary, they probably switch jobs. I mean, how many of you have probably switched jobs in the last 5 years? It happens all the time. So they do the same thing. And if you've got somebody from APT1, APT2, and APT3 all switching jobs, they're probably going to work with each other someday. You're going to have a mixture of TTPs, and you're not going to know who the hell it is. I mean, and then you're going to label it APT 41, 42, 43, and it's probably just the same old people you've been tracking for 10 years and you didn't even know it. So what's actually changed in our landscape? I think we've got a couple of big, really good things that happen. We've got mailing lists. Some of them, like CW and Yard Exchange, a lot of you are probably on them. A lot of meetups and conferences, just like this. I mean, DerbyCon is a great way to network and to meet people and to share information. There's smaller collaboration efforts, and there's something actually called the Cyber Threat Alliance. If you're not familiar with it, you should Google it, join it, get your company to join it. A lot of enterprises are realizing that it's not so much who's in your network anymore, it's someone is in your network. You get them out or prevent them from getting in. It's not always about, oh, we've got an APT3 actor, we need to call the FBI or call whoever to come in and take a look at all our logs. It's no, we've got something in our network, get it the hell out and make sure it doesn't come back in. And it doesn't matter if it's APT, ransomware, what it is. And I think a lot more people are getting smarter about that. And a lot more CISOs and people who are actually making decisions realize that it's more important to keep everything out and to keep our data safe than it is to figure out who's actually in the first place. Don't get me wrong. Pardon me. Don't get me wrong. It's important to figure out if you're being targeted, because being targeted is a whole other story. And if you are targeted, you want to know who that was. Another big change is certain things actually work. And as a community, we're learning what works and what doesn't work. There are a lot of products out there that smoke and mirrors. I mean, it happens everywhere. I mean, that's part of the game. So what I really want to talk about is automating. I like to automate a lot of the malware analysis I do if it's something that I've done before. A couple of caveats. Not every malware sample can be automated. A lot of things you're going to look at, you're going to say, oh, I really should write a script for this. And then you're going to be like, well, this is a custom payload. I'm probably never going to see it again. It actually has a couple of things in it that I know I'm not going to be able to script out for whatever reason. And that happens. You got to remember that people get paid a lot of money to create malware and to create code that you can't analyze, or that it's going to be difficult to reverse engineer. So then you got people like my boss here who actually does stuff like that for fun and then puts it out on GitHub. People get fucked either way. Yeah. So if you're going to repeatedly do something, you should try to write a script for it. If you're going to do this, if you have a piece of malware that you've looked at numerous times and you want to take notes on it, it's always good to make sure that you know certain things are going to happen with a certain malware family. But whenever you automate something, make sure that you verify the results. I've also worked places where people like to automate things and never check what actually gets pushed into the SIM, and you start getting URLs and domains pushed in there that are going to be on a block list, and all of a sudden you get a call because time.windows.com won't resolve because somebody blocked it. Happens all the time. Also, you should use other people's tools. If somebody's going to create something to help you or to help other people, make sure you're utilizing those resources. And if you write tools, make sure you share them if you can. I know there's some people that work in closed spaces that if they write something, it has to stay there. That's totally understandable. So how do I do it? I like to use sandboxes, like I said. It's always a first resort for me. They are not cheating, as much as anyone might think. Oh, I don't get to reverse engineer the malware, I'm not throwing in an IDA. It doesn't matter. You don't have to do that. You have to figure out what it's doing and how to fix whatever the problem is that somebody came to you with. Public resources, like I said, there's a lot of really good ones out there. You should always try to utilize them. Scripting, I would probably say most malware analysts out there, SOC analysts, IR folks, we've done a lot of scripting. Some people haven't. You might not have needed to, but you probably should get into it. DBI, dynamic binary instrumentation. Sounds a little scary, and a lot of people think it's black magic, but it really isn't. And I'm actually going to get into it a little bit and show a demonstration on how you can use it, how anybody can use it. And some automating debugging tasks. I have debugging scripts to do a lot of things for me because I spend a lot of time in a debugger. I enjoy it, but I also don't enjoy setting a breakpoint every time I need to stop on virtual alloc. I like to have shit like that done for me, and you should too. So, again with the sandboxes, about me and my job. So what I do on a daily basis is I actually look at code that will not execute in a sandbox. And what I like to do is figure out why it wouldn't do that. There's a lot of anti-analysis tricks, a lot of anti-sandbox tricks and things like that that people build into malware nowadays that are trying to specifically get around specific malware sandboxes, whether it's Cuckoo, the virus total behavioral analysis, or malware, whatever it might be. Sandbox hardening is probably one of the most important things you can do if you're using a sandbox. You need to make sure that you're looking for things that can make your sandbox look more realistic and make it look more like a real system, more like something that you would see on an enterprise, or like someone who might actually be interested in your network or in your enterprise, what they would be looking for. But how do you do it? When you're trying to figure out exactly why something won't execute in a sandbox, there's a couple of key things you need to look for. What code actually executed while it was in the sandbox? How do you do that? Well, what were the API calls that were made? So you can look at whatever API call was made, and whether that's a Cuckoo report that you're looking at, or whether you have some other kind of sandbox that you're going through, figure out what was actually called, and then look at the sample and figure out where in that sample those calls were. And you can pretty easily match those up and trace back what you were looking at. Where did the code stop executing? Again, look at your logs. figure out exactly where the code stopped, what was the last thing that got executed, and you should be able to go through and kind of match that up again with the malware. And also, are there any basic blocks that didn't execute that I actually want to see executed? And if that's the case, you need to figure out how to get there. And you need to figure out how to make your sandbox get there. And if you think you figured it out, you need to either patch the malware or write a proof of concept to test it and make sure that it works. So again, with the sandboxes, most of them all have free versions. Most of the ones that are out there, you can either get a demo from a company or you can find something on GitHub. There are a lot of different ones. Most people use Cuckoo. Cuckoo is probably the easiest to install and set up locally. And there are a lot of hardened versions of Cuckoo out there. You can actually do a Google search. I've got a couple of pictures up here on the slide that show the top 6 results if I search for hardened sandbox are different ways to harden your Cuckoo box. And I've actually gone through a couple of these sites, and most of them are all different techniques. And it's pretty interesting because if all these people have different techniques, you probably could implement those into your sandbox and have a pretty badass free sandbox. So again, like I said, with public APIs of these sandboxes, it's pretty convenient because you can actually write a script to query these sandboxes or to query these systems whenever you actually want to submit samples and pull back the results. So one example of this, I've actually taken about, I think it was about 35 samples that matched some core plug signatures that I had. If you don't know core plug, it's basically plug X. Hopefully you can see this. If not, I apologize. And all I did was submit them to VirusTotal through the API with a script, and I pulled back some results. And using VirusTotal's API, I was able to figure out pretty quickly which ones here that I would actually want to analyze. And if you couldn't guess it, the ones I'm going to analyze are the ones that don't hit a signature, because anything that's plug X, like I said, I'm never going to analyze that again. I already know that that's it. We should be able to figure out in some kind of automated fashion what the IOCs from those are. So this is just one of an example how you can take a large repository, you can submit it through the public API or any kind of, or a closed API, whatever you're using, and pull back some results that'll give you some pretty good ideas of what you're looking at. So, like I said earlier, public resources, we should definitely use these. So what happens if a malware author is writing a piece of malware and they explicitly use an array of bytes to make their strings? Well, basically like this. So one of the things you're going to see is you're going to see the strings being built on the stack with a series of move instructions. It's a complete pain in the ass. I mean, if you're an IDA, you're going to have to click M on every one of these bytes to change it over to an ASCII character and then try to read through and figure out exactly what this is going to be. So when I said public resources, one of the ones I use for this and one of the ones most people use is the Flare tool. It's a public Python tool that's available. It's called Stack Strings. And what it'll actually do is scan through your IDB. It'll scan through the current executable or whatever binary you're looking at. It'll look for these stack strings being built, and it'll create a little, basically a comment in IDA for you in your IDB of exactly what API call or what word was being built, because sometimes it might not be an API call, sometimes it could be anything. And this is just an example of how using a public tool can help you save you time in the long run. And I probably use this every time I see it, stack strings being built, because one of the things you're going to notice if an author actually uses this once, it's probably going to be in there a few hundred times, and that sucks. Thanks, Flare team, by the way. But that's too easy. Sandboxes and public tools, it's easy. I'm a reverse engineer. I'm going to look at low-level code all day. I don't need to use other people's stuff. I don't need to use sandboxes. So that's bullshit. If it works, it's not stupid. It's something that you need to take advantage of. You need to implement it into your tools, into your processes, and make sure that you're speeding things up, if that's a word, and making sure that you can get the job done as quickly as possible so you can move on to the next job. But you also want to make sure you're obviously doing it in the correct way. So if it works, you're done. Don't reinvent the wheel. And when I was a kid, we had tools like that. I grew up in the country. So scripting for RE. Experienced REs probably think, well, everybody should script, right? Everybody knows how to script. That's not the case. A lot of people that work in forensics or incident response or threat intel folks sometimes, even some younger malware analysts might not do a lot of scripting, and that's fine. The thing with scripting is anybody can do it and everybody should at least try. It's going to help you in the long run. If you don't know how to script, Google it. Google's awesome because Google can give you results from Stack Overflow. Stack Overflow is pretty much how I learned how to script, and I know a lot of people have done the same thing. You don't need a computer science degree to script. And it can help you save time in everything, not just reverse engineering. So what should I write a script for? The obvious things. You've got string deobfuscation, file parsing, IAT root building. I mean, this kind of stuff, I mean, everybody does this. It's almost a necessity. But some of the not so obvious things are file patching and bulk data analysis and deobfuscation. So I've got a demo that's going to explain, it's going to show a little bit of the bulk data analysis. And the demo that I'm going to show you is actually from a campaign from 2016. And any of you folks that are working at threat intel or malware analysis might actually remember this one. A group, Unit 42, actually wrote up a blog on it. It was a net traveler malware that was targeting a few different people. I'm not going to get into that. And essentially what it would do is it would write a malicious, it would write an obfuscated configuration file to disk, and it was supposed to delete it, but it never actually did. And in this config file, one of the things that you'd see are different fields, U00P, K00P, and a few others. And one of the fields was actually an obfuscated C2. So we've got a C2 that we know that's being written to disk, and the C2 is actually going to be called out to. So one of the things that at the time where I was working, threat analysts would ask me is how can I get this C2 without having to give you every single one of these files that I'm looking at? Because we'd actually find a lot of new ones, and it became a pain in the ass. The particular variant would drop these files. Sometimes it would attach them in malware or in email messages, and you would see them as a self-extracting RAR. Basically, you would have a config file, you would have a DLL, and a legitimate executable. So if that sounds familiar to anybody, that's like a side-loading malware. We see that all the time. So as you can see, one of the first things I wanted to do was figure out where that obfuscated C2 was located. And this image right here, you can see I think it's FSA or FSLAPI.dll. This was the DLL that was actually dropped to disk, so that was being side-loaded into the legitimate executable. And down at the bottom, there's the config.dat. That was the file that was written to disk. So I know that the information I'm looking for in the config.dat was the U00P, and you can see the bytes after it, 72, 7F, 80, etc. Those are actually the bytes of the obfuscated URL. And I did a couple of searches just for the hell of it in the DLL, and I found the exact same string. It's actually located there. It's pretty easy to spot, and I'll actually show you when I bring the demo up. So I knew immediately that every time that I saw this, I wanted to check the DLL and see if I could find this string. It just so happened that I could. Just real quickly, I was looking for a bunch of these samples, so I wrote a really crappy YAR rule, but it worked. And to point out, the string 2 essentially is just the encoded http://www. Because that is the beginning of the URL that they used every single time. So if you wrote a YAR rule to look for that, you'd find every one of these samples. The DLL Shanghai.dll is just the internal name that these actors used for the DLL. Okay, the demo. Let me have to end this real quick. Okay, hopefully you can all see this. Resolution's awful. So I've got two folders up here. Yeah. So in the top, it's basically the contents of one of the self-extracting RARs, and at the bottom I have the same thing. And they both have the config.dat file that was written to disk. And what I want to show first is that in the DLL, like I said, if I bring it up in a hex editor, yes, I use Explorer. I love it. It works really well. You can actually see in the bottom of the DLL, that is the beginning of the obfuscated C2, and it's in every single one of them. So you don't have to find all these files and all their components. All you have to find is the DLL. Made it really easy to do this. The temp.bat is what was supposed to be written to disk to actually delete the configuration file, and this one actually didn't drop one. So the config.dat file, like I mentioned before, it actually has the U00P field, which is the same encoded C2. And one of the other things I wanted to show is the blog that was actually written, and I don't really care about the contents. I mean, it's really good. I'd highly recommend everybody read it, yada, yada, yada. But the thing is, if somebody writes a good blog, they're going to leave you some good information. And right here at the bottom of the blog, we've got the decoding algorithm, the decryption algorithm for the C2. So you don't even have to look at the code. You can find somebody else's work, and if you're trying to track these guys yourself, you can do it. You can actually pull this algorithm and you can write a tool. It's really easy. The script that I wrote is not very big. Actually, where is it? Oh, here we go. So this is the folder containing all the files that I actually had that I was working when I actually did this, when I was working threat intel at my previous job, and I actually had to reverse these samples. These are the ones that were actually given to me that were found in customer networks, and these five are ones that I actually found on a VirusTotal retro hunt. So that means in the last 3 months, these files were recently uploaded to VirusTotal. I'm not saying they're new, because they're not, but it's still kind of interesting that I got some results. So my script, if I run it, all I'm doing is searching through every one of the DLLs, looking for that encoded string, and I'm going to print out the hash, and I'm going to print out that decoded URL. So some of these URLs might look familiar, but what I really want to show you is the fact that it's not difficult to do this. I simply implemented that subtraction algorithm that was put into that blog. I have a function here called find it that essentially searches through the group of files that I had, and it was going to look for anything that had the beginning and the end of the encoded algorithm, or the encoded C2. I did a hashing of it, and I printed them out. Very simple. But the thing is I can take this and I can give it to an analyst, or a threat analyst, a SOC analyst, somebody who may not want to go through and reverse engineer these samples, and they can look at it whenever they want. They can take Yara hits, any kind of signature hits. They can run them through here, pull the C2, and add those to whatever list or documentation that they might need. So let's, yeah. Did that work? Yes. Okay. Just don't have my mouse. Cool. So dynamic binary instrumentation. So it is a difficult subject. I'm going to briefly discuss dynamic binary instrumentation. To get technical, it's application level modification of code in memory at runtime. That's a lot. Essentially what happens is you inject instrumentation code into a binary during execution. Again, that can be a lot to soak in. But really what you're doing is you're watching every single thing that happens when that binary executes, and you're able to modify the execution because you have instruction level access. So every instruction that's being executed, you get to see and you get to monitor, and you can set up any kind of callback functions or anything that you would like before those instructions actually get executed. So I use PIN. There are a lot of other good tools, but I use PIN because I can write a DLL in C++, and to me that's easier because I understand it. I'm not a good coder at all. I wouldn't even consider myself a coder, but I can do it. There are many examples included in PIN, and that's mostly how people get started, because with the example code that you get, a lot of times you'll be able to modify a couple of lines of code here and there and very easily create a new PIN tool that can be useful for you. I would highly recommend starting to use this by modifying some of the example code. So one of the reasons I like PIN, like I said, lots of examples, it works for me, and it's been very efficient, especially with running a lot of executables. So I'm going to go through a simple example of some of the things that I do with PIN. This one's very basic, and all it's going to do is hook a couple of API calls, or actually one API call. So while this loads up, a little bit of background on this particular demo. I wrote two small applications, faux malware you could call them. The only reason I did that is because I wanted something very simple and very compact that I could use as a POC. This particular API call and this method that I'm actually going to show, the reason that I came up with this was because it's the same one being used in some Hansiter files. So if you're familiar with Hansiter, it's a malware family that is doing pretty much this exact same thing, but I didn't have enough of the files to have a decent demo. Anyway, so essentially what I did was wrote a pin tool that's going to go through all these malware samples that I have here, and it's going to hook the API call, or it's going to monitor the arguments, I should say. It's going to figure out when the API that I'm looking for is actually getting called, and it's going to pull the arguments back, tell me what they were, and in this case it's going to be Internet Open URL A. And if you're familiar with that at all, the first argument that gets sent to it is a long pointer to a zero terminated string that is a URL, and that's what I want. I really want that URL. So before I click enter on this, one of the things that I've done is every time that one sample is executed, it's going to write a file to disk, and it's going to save that C2. And it does that for every single one of these. In the end, I have it cleaning it up, but the reason I have it saving these to disk is so you can see how long it actually takes to execute each file. So instead of having to do dynamic analysis in a sandbox, or run each file and then take another snapshot in your VM, you can do something like this, and you can literally go through these in a matter of seconds. So as you can see, we're going to wait a second here and let all these execute, and we'll know when they've executed because all these text files are going to be created and then they will get deleted. And like I said, you can see as they're created, that's how quickly that I'm actually executing each of these samples and hopefully pulling back some data. Let's see. This VM, no, this is a very basic VM. I don't really have much going on in it. This isn't actually Answer. These are some files that I made that act similar. Yeah, these are just test files. Yeah, there are some startup things that will go on in the Answer to DLLs that you actually need to do some patching for. So it was easier to write a couple of quick demo samples. That is true. That's okay. So this is the results. Let's hope I get something here. Okay, so again, these are fake URLs. These are just things that I wrote into the samples. As you can see, I've got sample 0, sample 1, 2, etc. in the hashes. So I was able to pull the API arguments, which are good. That's what I was actually looking for. But what's more important is how I did that. And essentially, I'll get into the pin code here in a second. But all I wrote was a simple script with Python subprocess that's going to execute pin for me every single time when it iterates through a list of files or in a folder. And you can do that with any executable. It doesn't have to be pin. It can be any, basically anything you want to run on a file. So what did I do with pin? To start, I had two unique groups of malware, like I said, just fake malware, but in a sense this could be used on anything. They both used Internet Open URL for comms, and that's what I was trying to pull arguments from. And the pin tool itself, like almost all pin tools, you'll create a callback function, and what that means is it's going to find all the it's going to look for the calls for this or for any instruction that you're actually writing the callback function for. So for me, I had to find all the calls to this API, and I wanted to return the arguments. And once I parsed the argument that I was looking for is actually the URL, which was the first one, so that was pretty easy. And this is a very basic tool, but it serves its purpose because I'm able to get IOCs from different malware samples, and I don't actually have to execute them all, or if I wanted to, I could actually push them to some kind of automated system and let them execute this themselves. So the pin code. This is what some of the most important functions in a pin tool look like. There's a lot of included code in a pin tool, but most of it you're not going to modify. I basically added two things. The first thing was the top function. The top function basically is just going to find all the calls to the Internet Open URL. You can see that. And underneath it you see the, basically it says funcarg, and it goes all the way down from 0 to 5. That's the 6 arguments that Internet Open URL is actually going to take. And the one I end up being interested in is the first one, 0. And you actually have to choose whether or not you want to pull information before the call executes or after it executes. And this is very simple to do because you can either modify the before or after function that gets called. So I wanted the before, so you can see in the bottom bit of code there, you can actually see what's going to happen if that before function gets called. And what it's going to do is it's going to put types to the different arguments that were pushed. And you can see the different, I can't really see it on mine, but you can see that the LP, I think it's SZURL, is the first function, or second function. The first one's actually the handle to, yeah, it's the internet handle. So the second function is actually the one I was interested in, and that's what I had pulled back. Trace file, again, at the bottom is basically just going to modify the output file that gets created. And so as you can see, I created, or actually modified, two very simple functions, and it's really not difficult to do. PIN isn't black magic. It's not something that only certain vulnerability researchers or advanced reverse engineers are going to be able to do. Anybody can do this kind of stuff, and there's a lot of open source PIN tools out there. A lot of things people create and they share publicly. But what if I actually have to reverse engineer something? There's ad hoc automation. A lot of times people write some string deobfuscation scripts. You've got IDA Python. Highly recommend using that. Or if you use binary ninja now, you can use Python right in there to deobfuscate things. You should always look for compressed code or encrypted code inside of a binary, and if you can somehow decompress or decrypt that before actually running the malware or analyzing it, you can speed up a lot of time. There's a lot of times that I'll look through code and I'll see something that's got maybe a zlib compression, and once I decompress that data, it's actually going to be shellcode that is pretty much the entire payload. So instead of analyzing the wrapper around that, if you can decompress some code and figure out what's actually going to happen in the end, you can save yourself a lot of time and a lot of hassle. Another thing I like to do is create a lot of debugger scripts. It's very useful, and I'm always in a debugger, so if I can speed up my debugging process, it saves me a lot of time. I'm going to talk a little bit more about this. So with debugging scripts, they're very helpful with dealing with malware, especially if you're looking at the same malware over and over, because you can speed up a lot of things, like I said. There are a lot of different debuggers you can use. I prefer WinBag, however you want to say it. You can use WinAppDebug or PyKD and IDA Python, Ali Immunity. They both have their own Python implementations. There's a lot of different ways you can speed up debugging with scripts. If you're still doing BU kernel 32 virtual alloc every time you're in WinBag, you're really slowing yourself down. I wouldn't do that. But always check MSDN, because there's a lot different. There's a lot of differences between a kernel base and a kernel 32 when you're setting a breakpoint. There's certain ones that are actually going to work and won't work, and if you do that enough, you're going to realize it. Plus, things are spelled a lot differently. There's, again, a big difference between a load library A and a load library W, and you need to know those. So a quick demo of, let's see how I can, so this might take 1 second. I need to revert a VM. There we go. Apologize about the resolution. It's not what I had planned for. So basically what I want to show is something related to a blog post that some of our folks at Unit 42 actually just put out. There was a malware sample they were looking at. Don't remember the family off the top of my head. It had some DLLs that had exports to it, but the exports didn't have any names. And if you've looked at the recent IDA update, you'll notice that from IDA 6.9 to 6.9.5 actually fixed that bug. So the malware itself didn't have names for any of the exports, but it still had exports, and people were interested in those exports. When we were analyzing it, we could see that certain exports were being called by ordinal number instead of name, which can be confusing because if you're looking at the code in IDA, you're not actually going to see export names. So for an example, this is the particular file that didn't have any export names. And you can see, looking at the exports, looks completely blank. So this is IDA 6.9. I do not have 6.9.5 installed, or I would show you what it looks like now. So I use WinBag a lot, and in WinBag you can do some simple things like show exports on a DLL, and it's going to show you the exports of that file. So this is an example over here. The malware.dll that I've loaded in here has 3 different exports to it. You can see the service main, debug create, and debug connect. And you can either check these with the show exports built-in bang command, or you can do an examine of the DLL with a !*. So if I load the same file that was blogged about into WinBag, which is the qpbqxr _dat, which you can see right here. First thing you should notice, it says no symbols, and I reloaded this twice, so I still didn't get any symbols. It doesn't have any exports that it's going to show me, and I can test that. Oh, I need to give it a name. Okay, if I do show exports, I get nothing. What if I examine this DLL? So let's look for the exports this way. Again, I get nothing, which kind of stinks because I know from some analysis that it's actually exporting a DLL. So what if I want to find some exported functions for this? We should all know how to do this because where are the exports located? They're located in a file header. So a real easy way in WinBag to get this information is we can do a dump header on the offset, so the base address of this DLL, which we can see the base up here in the load modules. So I'm just going to do real quick. And attack F to shorten it up a little bit. So what we see here is we see an array of image data directory structures. And the one we're interested in is going to be the export directory. And the export directory, it shows it's actually at 4,000. So if I want to get these exports, I need to keep going. And I'm going to take a look at what's at 4,000. So dump the contents of this space. And this is my export directory. So if anyone remembers what an export directory looks like from analysis, this is what we've got. But we don't all remember what that looks like. So I will show you. Come on. This is the image export directory. You can see on the right-hand side, I actually have a picture of the one that we just saw in WinBag for this sample. In pink, I have the D words, and in orange, I have the words actually highlighted, so you can see them a little bit better. And in green, I have the 3 that I'm in, the 3 addresses, the 3 offsets I'm actually interested in. You can see it's the address of the functions, the address of names, and the address of the ordinals. What we want is the address of functions because we already know there aren't any names. And one of the other things I'm interested in is the fact that it says we've got number of functions, and that's actually a D word. And if you look at it here highlighted in pink, it's 1 spot over from the first green block. It says there's 5. So it says there's 5 functions available and 5 names, which is really not true because we don't see them, but they're there. But anyway, let's go back to the demo, and we can see this is the exact same export directory, and what we were interested in was the offset of the functions. So the offset of functions looks like it's 4028. So if I just take a look at 4028 and see what we have here, this should be a list of the 5 exported functions from this DLL, hopefully. But how do we know? We can cheat. There are a lot of tools out there that actually do this right. One of the ones that I use is CFF Explorer, and with CFF Explorer, we can actually bring up and see the addresses that it's showing here. So I can make this a little bit more visible. Shows that the first is 2501, second is 2575, then 1B13, etc. And it looks like those are the same ones that I've got in this export directory, which shows me that those are the exports. From previous analysis, I know that 2575, or the ordinal 2, is the one that was being executed. So just out of curiosity, before I did anything else, I would make sure there's actual code there to make sure that this is probably the entry point or the point of execution. So if I disassemble it, I see a proper prologue, and I see that it probably looks like a function that's actually been executed. And if you're not familiar with this, this is what a function looks like in x86 assembly, at least the prologue and the beginning of the function. So that was kind of a pain in the ass. So what happens if you don't want to go through all that? You script it out. I was talking about scripting the whole talk, so one of the things that I like to use is pykd, and it's real easy to load up. You can do a load pykd.pid. You just got to make sure you have it in your extensions directory. And the script that I wrote for this is basically going to find the information that I just showed you how to get, but only it's going to do it itself. Oh, forgot. I have to provide an argument. So I was able to write the script to give us the entry point. So if you want to break on the actual entry of the DLL, which would be DLL entry, or if you want to, you can actually go down and see all the different export addresses. And the one that I was interested in before, like I showed you, was 2575, which was the second ordinal, or the second function. I've also got the LP addresses up here just so you can have those if you ever need them. This is a very, very easy script to write, and it's something that I'm going to be able to reuse every time I look at a piece of a code that's a DLL. And to give an example, or just actually to show you what it looks like, I've got two examples up here. And one is a really crappy piece of code, which is over here. This is the first one I wrote. Basically, where'd we go? And basically, this is a linear program with 0 functions, no modularity, and it's really going to be difficult for someone else to utilize this. And over here on the left, it's more of a modular design where I have functions that I can reuse and put into other code if I needed to. And I just basically wanted to show that if you're going to write a script for something and you're going to share it, make sure you make it something that people can understand, read, and reuse, because no one's going to take the one over on the right and have a clue where they can borrow this or reuse it at any point. But over here on the left, if you need to parse a header, you're going to be able to see what pieces of that header you're getting back and how to modify things with it when you actually do return values. So those are pretty important. You don't want to be releasing code to the public that's going to look like garbage. So again, what did I do? I walked the export table in WinBag, it's not too difficult. It's maybe 5 or 6 different commands. But even before you get there, you got to find the entry point. You can either walk the PEB, or if you want to, you can just do a load module, look at the base address that way. But either way, you need to be able to do at least 5 or 6 functions, 5 or 6 different commands to be able to get that information. And whenever you have to do that many commands to get something that's common throughout multiple files, it should be automated. It should be something that you do one time and just load up a script or load up some kind of tool. So why did I automate it? Like I said, I wanted it to be quick. I wanted to be able to reuse this and not have to worry about it in the future. So automating reverse engineering, it doesn't have to be fancy. It's something that anybody can do, and just because it looks easy and it seems simple doesn't mean that it's a bad idea or that it's not useful. Everything you automate should always be something that's repeatable. So if you're doing a task and you're only ever going to see it one time, or somebody writes a piece of malware that's going to come into, it comes into your system, and you look at it and it's dealing with particular shared drives that you have on your enterprise, I wouldn't try to automate that. I would probably dive down a little bit deeper. Or if you're looking at a piece of malware that's specifically targeted for you, again, I probably wouldn't automate it, because if you get hit by it again, you've got other problems. The data should be transferable, and what I mean by that is it should be modular if it's code. If not, it should be something that you can give somebody confidently and say, hey, you can use this, I can use this. Or if I've got a threat analyst that is interested in it, they shouldn't have to try to read 5 or 10 different documents to figure out how to use it, and they shouldn't have to reread my code. It should be pretty easy for them to understand and figure out how to use, and they should be able to get the information they need by using that tool. And it should be shareable. I highly encourage everybody to share things if you can. I know in an ideal world that would be great, but a lot of people work for cleared folks and different agencies, and that doesn't always happen. So why isn't automating reverse engineering tasks easier? Well, you've actually got to know stuff. Some of the things you need to know, and this is very basic. If you're a reverse engineer, you think, oh, well, everybody should know how to do this. But like I said earlier, not everybody who's looking at malware and doing malware analysis is a reverse engineer. So you need to be able to do understand basic file headers, PE headers, bitwise operations, some basic crypto. I mean, it's very easy to determine when you've got a RC4 algorithm and you've got some kind of S-box creation being done for an RC4. You can read up on that, but in general, basic crypto routines like that are things that you should be able to identify in code, and you should be able to implement those and re-implement them. You should know the different nomenclature types and the types of data. If you're writing in Python, you need to know what an ordinal is. If you need to know how to typecast things into a character and into hex and understand how these work behind the scenes. You need to know an actual scripting language. You can't just say I'm going to automate things and then start writing in Perl Python, because there's no such thing. You need to pick something and learn how to use it. Calling conventions are always something that you need to know. If you're manipulating data that's coming from the stack, or you're pushing specific data onto something or to a stack, or doing anything like that, you need to know how it's working. And if you're going to use DBI especially, you want to know where the arguments are coming from and how they're being manipulated. A couple of words of wisdom. I always tell people, if the sandbox can do it, you shouldn't have to. Please don't reinvent the wheel. And if it's repeatable, don't repeat it. Do it one time and let something else repeat it for you. Are there any questions? Yes? That's what? Mm-hmm. I would not admit that. No, because if it's recompiling itself, it's so more like a polymorphic memory recompilation. So something like that, you're most likely not going to be able to, because if it's recompiling itself in memory, it probably has an algorithm that's going to change things up. And unless you're going to figure out what that is, you're probably not going to be able to create a script or any kind of tool that's going to do it for you. You're most likely kind of screwed. It's something like that's almost like a DGA. Once it gets created, you need to find the algorithm, figure out how it's going to work at a different level. Yes? I am. I'm going to clean it up a little bit, and I'm going to put it on my GitHub that I think I just created the other day. I've never really used it, so it will be up there.
So using dynamic it makes it really slow. It's really slow. You said any malware that will actually have a timing attack?
A lot of malware will check for the timing attacks. Or do timing checks to look to see if something like that's being executed, and that happens in sandboxes and all the time, which is one of the things I said at the beginning. It's actually pretty cool to look at the malware and figure out when it's doing that and stopping it from doing that. And if you can do that, then I mean you're at a whole new level at that point. You can manipulate the malware. I mean the malware author's already done writing this stuff. Now it's your turn to kind of rewrite it and tweak it a little bit and make it do what you want it to do. So you can, if you want, you can go in and patch that out so it doesn't happen again. Throw in some no ops or whatever, and then actually run it through the DBI. And you're good to go. Yeah. Have not. I should. Sounds fun. Yes.
So some people are looking at the idea of ignorant computers as anti-hacks for malware analysis. Does that sound like a conversation here?
Like setting up an ESXi server or Docker or something like that? Yeah, I think it's awesome. Most of the places I've been in the past, we've tried to do that, and it works really well, especially if you set up, I haven't used Docker, I'm kind of just new to it, but we used to use ESXi, and you could actually set up multiple VMs, and each VM would work for a different malware family, and you could have different scripts set up in each VM, so then you could automatically push different samples based on signature hits into those VMs via the ESXi API. It worked really well.
So Docker's actually like specific. So you're thinking about like there are like line
Possibly. I haven't messed with those at all, but I'm sure that's possible. Nothing else? Thank you very much.